Okay. Good morning, everyone. Welcome to the beginning of our Thursday press program here at the 227th meeting of the American Astronomical Society in Kissimmee, Florida. I'm AAS Press Officer Rick Fienberg. I'm assisted this morning by my two deputies, Larry Marshall and Inga Heyer. Larry will be manning the microphone for the Q&A, and Inga is watching the webcast. For those of you who are on the webcast, just a reminder, if you have any issues, please use the text chat to let Inga know. And when it's time for the Q&A, please use the text chat to ask your questions. Quick announcement for any of the press registrants who were at the dinner last night. I sent you an email this morning. If you didn't receive it, please come talk to me. I'll tell you how much you owe me and how to get a receipt. We had a really good time last night. So this is not a press conference per se. This is a seminar for science writers, which means that it's more of a backgrounder, an opportunity for science writers to learn about a project, learn about some scientific areas of inquiry and how they're being addressed, with the prospect that eventually you'll want to write about it. And this one's special because it includes a very interesting opportunity for science writers, as I'll explain at the end. So the topic this morning is science from SOFIA. SOFIA is the Stratospheric Observatory for Infrared Astronomy. It's a project, like all big astronomy projects, years in the making. It's a 2.5-meter telescope carried in the back of a modified 747. It's a very large telescope in a very large airplane. And the airplane acts as the mounting, for the most part. The direction of flight determines the direction that the telescope can look. The telescope can look high or low through a huge opening the size of a big garage door in the back, and the airplane is miraculously able, thanks to very good aeronautical engineering, to fly very stably and very quietly, straight and level, with the telescope pointing with the kind of pointing accuracy that you would get from any ground-based telescope. SOFIA is primarily an infrared instrument, or an infrared telescope, though it does have some optical instrumentation that you'll hear about this morning. And rather than line up a bunch of NASA suits to tell you about their project, we've arranged this morning for four astronomers at different institutions around the country who have begun using SOFIA. SOFIA is now operational. It's flying year-round. It's flying out of NASA Ames in California, and it's made a couple of journeys. It's flown out of Germany in Europe. It's flown out of New Zealand in the Southern Hemisphere. It's mobile, so it can go anywhere, and that makes it especially suitable for observations of transient phenomena, things like occultations or eclipses and things of that sort. So the four speakers that we have this morning are Robert Gehrz from the University of Minnesota. He happens to also be a AAS past president, so we're honored to have you here today. He's going to be speaking about SOFIA FORCAST, which is one of the instruments, Grism Spectra of classical Novae. Kate Sue from the University of Arizona will talk about what SOFIA observations tell us about planetary debris disks. Graham Harper from the University of Colorado in Boulder will talk about Betelgeuse, the bright orange star in Orion, using SOFIA as a thermometer to probe where it matters. And then Michael Person from Massachusetts Institute of Technology will talk about observing Pluto's atmosphere with an occultation just this past June. Now, as I said, it's more of a backgrounder. None of them are going to unveil dramatic new scientific results, but there is a SOFIA science session this afternoon at which they will be getting into some more detail about some of the scientific observations they've been making, so I encourage you to drop in on that if you get a chance. So as usual, even though it's not a press conference per se, we're going to have all the presentations in order from right to left, and then we'll take questions at the end. One final reminder, please silence your beeping devices, and we'll get underway. So I will turn it over to Bob Gehrz. Let me just make sure we can find presentations. There they are. All right, great. All set.
Thank you very much. I'm going to tell you a little bit about some of the science we're doing with SOFIA at the University of Minnesota, where we lead a giant consortium of people who study classical novae. We've been studying these for a long time, almost 40 years, and the reason we do it is because they are stellar explosions that contribute in some material way to the chemical evolution of the universe. So I'll tell you a little bit about how novae are related to galactic chemical evolution. We'll show you what a nova explosion actually is in some way, and then we'll talk about the kinds of things that we're able to observe about classical novae in the SOFIA era. We're able, with this new observatory, to extend the kind of observations we've been making into a much more active regime. So here's a classical nova explosion speeded up by a factor of 1 billion. The events you're seeing here actually take about 100 to 1,000 years, and you're looking at a binary star system where one of the stars is an evolved star that's become a white dwarf. That's the little thing there. And the other star is one that's more like the sun or maybe a red giant, and it's starting to swell up as it expands in its later lifetime, and the material from the atmosphere of that star is flowing down onto the white dwarf through the place where the gravity of the two objects is equal. So it accretes onto the white dwarf. Now the star that's blue in this picture that's adding the material onto the white dwarf is rich in hydrogen. A white dwarf is made out of stuff that can't burn, carbon and oxygen maybe, or neon is in there. So when the hydrogen layer builds up to about 2 meters in depth, the temperature at the bottom of the layer is high enough so that the hydrogen starts to burn, but the layer is degenerate the way the material of the white dwarf is. And the way the physics of gases like that works, there's a runaway explosion that actually happens in the space of a few hours. The light from as the hydrogen burns, it gets hotter and hotter and hotter, but the way degenerate gases work, the hotter they get doesn't mean that they create more pressure the way a regular gas does. And so after a while, the light gets to the point where the light itself is so bright and the pressure from the light is so great that it just blows the material back out off the white dwarf. So while this burning is going on, all sorts of new chemicals and isotopes are made, and the explosion expels this stuff into the interstellar medium. Now, you probably heard about the Big Bang. We think it only made hydrogen and helium. So we want to explain how the other 90 elements that we find evidence for in the periodic table came into being, and we think this happened during the process of stellar formation and evolution. And here you see in the picture a little cycle that represents stars being born and dying. Well, novae are in the dying phase. They're expelling material that goes back into the interstellar gas to become part of new stellar systems and new stars. So in a nutshell, here's the way the evolution goes. New elements are synthesized in the explosion. They're ejected into the interstellar medium where they become parts of new stellar and planetary systems. And then in the infrared, that central engine, that white dwarf, remains hot. It heats up the expelled gas so we can see emission lines from the gas. As the gas expands, it cools off and dust grains can form. Those are the building blocks of planets. And so we can actually see the thermal infrared emission from the dust grains themselves. So the first thing we are going to do with SOFIA is learn more about the dust that's made in nova explosions. And SOFIA has these Grism spectra, Grisms. They're a prism that has a grating ruled on it, so you get high dispersion spectra. You spread the light out and you can see the different wavelengths. And we can diagnose all the different kind of minerals that are in the dust using these Grisms that belong to the FORCAST instrument. And so far, what we've learned from other studies is that novae produce all the different kinds of astrophysical dust we've ever seen. Carbons, silicon carbide, silicates, hydrocarbons. Well, with SOFIA, we're going to have the spectral resolution to learn more about the detailed mineralogy. We'll be able to figure out how much of the dust is amorphous, that is made under low temperature conditions. We'll see how much of the dust is crystalline, made under high temperature conditions. We can get the mass of the dust, and we can also get the mass of the gas from those emission lines, and so we can actually work out the abundances of things like carbon and oxygen. Already we know that carbon and oxygen, building blocks of life, are 20 times more abundant than they are in the solar nebula from studying novae in the past. We can see more lines with SOFIA and learn more about the abundances. Here's an example of a couple of these emission lines I was talking about. These were obtained with a spectrometer on the Spitzer Space Telescope. that some of you might have heard about this morning in Giovanni Fazio's talk. We learned from this particular spectrum you see in this picture that the Nova QU-Vel had about 170 times more neon in its nebula than the solar nebula has. In the solar nebula, there's one neon line for every 10,000 hydrogens. In this nova, there are about 2 neon atoms for every 100 hydrogen atoms. So we're learning that novae could be very strong sources of things like the building blocks of planets and life. Carbon, nitrogen, and oxygen, and certain isotopes of those could be produced in very great amounts in nova explosions. So with SOFIA, we open a new era in the study of nova explosions. We can see lines that you can't see from the ground. We can see more lines with these spectrometers than we were able to see with the Spitzer telescope because of viewing constraints. We never got Spitzer on some of these things in time to see all of the lines we can see with SOFIA. James Webb Space Telescope doesn't go to the long wavelengths that Spitzer goes to, and it has severe viewing constraints. So SOFIA is really going to open a new era. And I'll just show you this first spectrum that we got of a nova with SOFIA Grisms. It's a hydrogen spectrum. It was early in the explosion. We didn't see evidence of the more exotic elements yet, but that's the first time we've ever seen all the hydrogen lines from 3 microns to 30 microns in a single spectrum of a nova. And every one of those lines that you see in there against the continuum is a hydrogen line. So the summary is that the SOFIA flight cam, the FORCAST Grisms, which I'm going to talk about this afternoon. Flight cam is another instrument that can see another part of the spectrum. We'll use it too, but with the FORCAST Grisms, we really cover all the wavelengths that you need to cover to see the entire story about the mineralogy of the dust formed in novae and the gaseous materials that are formed in the spectra, and we'll get abundances of the gases too. So thank you for your attention. Later we'll answer questions.
Reset. Okay, so what SOFIA observation can tell us about planetary debris disk? My name is Kei Su. I'm a research faculty from University of Arizona, and I consider myself very fortunate to have this opportunity to use all this great facility to study planetary debris disk. I'm mostly using Spitzer and Herschel observation, and now kind of extending to using SOFIA and ALMA. So, in a nutshell, what are debris disks? They are thin, dusty disks around stars that made of material that left over from the formation of the star and its planetary system. So, in this illustrated view that you see on the diagram, the star is at the center on the left, and it may contain fully grown planet already, either giant planet or terrestrial planet, as shown in the graphic here. And some of the leftover planetesimal, kilometer-sized body that's showing as this big black dots over there. So in a typical planetary system, in addition to this, the planet and the planetesimal, another very important ingredient is dust. These dust particles are generated through collision of this leftover planetesimal. Just for analogy, in our solar system, the asteroid and the Kuiper belt are the two leftover planetesimal population. So the dust is generated through the collision between asteroid or Kuiper belt object, or from the cometary activity. They will spray out the dust all along the system. And because this dust particle cover a huge surface area, they are actually the most easy observable component in a typical planetary system. They are much easier observed from their parent body, like the planet and planetesimal. And this dust particle can scatter light from the star, so they be invisible in the visible wavelengths, or also they can be warmed by the stellar radiation and re-emit that energy in the thermal infrared. And the resultant emission for those thermal emission, they peak at different wavelengths, depending on their dust temperature. If the dust is closer to the star, they are warmer, so the peak emission emit at shorter wavelengths. So the emission is depending on the dust temperature. So in order to get a complete picture of this, the planetary system, you really need to have a full wavelength coverage from the near infrared all the way to far infrared, some millimeter. So generally speaking, for SOFIA, I'm using for the debris study, they are very sensitive to probe the terrestrial hot dust, roughly 500 K, and the astral-like warm dust around 1500 K. The hot dust, they are particularly very interesting because you can use them to study terrestrial planet formation. We know there's a small fraction of young 10 to 200 million years very bright debris disk that is known to have a large amount of the terrestrial hot dust, where a variable disk emission and permanent solid state feature that you see on the diagram suggests that they are active site of a large asteroid impact in the process of forming terrestrial planet. And we have an ongoing Spectra program trying to monitor this variable disk emission photometrically, but we can't do it spectroscopically because Spectra ran out of cryogen. So, and we are very happy to learn that we are going to do a spectroscopy with SOFIA, just like the one that Bob mentioned, using the FORCAST Grism spectrum. And this observation will be very valuable because they will bridge the gap between the past cryogenic Spectra mission and the future GWST observation, providing a long-standing documentary legacy value. So I'm very excited that I'm going to get some of the spectrum with SOFIA this summer. Another primary interest in using SOFIA is trying to resolve the nearby debris disk emission at 35 micron, a wavelength that is not accessible from the ground. There are many, many reasons why you want to resolve a debris disk structure. I think the most attractive one is that this structure can reveal the presence of planet. And back in 1999, this paper by Liu and Zook, they did some calculation in terms of the dust particle distribution for the solar system. They quickly realized that our 4 giant planets are preventing the dust particle in the Kuiper belt entering the inner solar system. If the solar system didn't have that 4 giant planet, the dust particle from the Kuiper belt, the outer ring, will drift inward and filling out the interior space. Just like the graphic showing on the other side, you will have a Kuiper belt dust ring and then have a flat dust distribution interior. Because the temperature dependency I'm talking about in the earlier, this is the dust particle distribution. But what your observation has this temperature dependency. So when you look at a system with one belt with a planet, you see a narrow